Welcome back, everybody. It is a pleasure to introduce to you Chaim Goodman-Strauss from the National Museum of Mathematics in New York. As many of you know, he will give a second more public talk in a couple of weeks, but today he's going to talk about complexity in tilings. And you're very welcome. Over to you.
Thank you very much. Thank you very much for having me here as a representative of the hat tile and its recent discovery, but also it's nice for me just to sort of check in with what's been happening with geometric packing. It's been quite a while since I've been at a meeting focused on this, decades in fact, and just nice to sort of see what's going on. So I am recently at the National Museum of Mathematics in New York, which is a complete career change and very interesting one, but also I just want to advertise sort of rather shamelessly that I'm available. So I could, for a short or long stay.
Could you just briefly say what a National Museum of Mathematics is?
Sure. So it's what it sounds like. It's got the world's largest number. No, it's it's a sort of a science museum in the style of today's museums, where it's all hands-on and kids come in and they explore a lot of sort of interactive things that illuminate various mathematical ideas.
So it tends to be aimed at young people.
And what I didn't really realize until showing up there is that the key demographic is about 5 years old, but we have all kinds of programming for all sorts of things. So a lot of my time is spent unloading school buses, but it's great because it's important to tell people about Mobius fans and things like that. I have a good time.
You're getting the right demographic. It is the right age.
It's great. It's great, but my job is going to be considerably more flexible. Apologies to you had to put up with all sorts of.
Can I ask one other question?
Yeah,
it used to be known as MoMath.
Oh, it is MoMath.
Yeah, so it has a nice,
that's right.
allusion to another art institution.
That's right. So on Wednesday, 2 weeks hence, I'm giving a talk that's supposed to be more publicly focused, and so because of that. That's kind of the introductory talk. So there's going to naturally have to be some duplication, and I just apologize in advance for that. And at the same time, some ideas I'm going to just postpone until then. So, but what I wanted to talk about in this context is the complexity of tilings, and just sort of raise a few issues that are sort of I think that have always excited me about the connections of fitting together these shapes with the theory of computation, and I think in some ways it's interesting to me too. It's sort of the exact opposite of not really, but I mean it seems like a lot of things here. I guess either some of you are paying a lot of attention to the combinatorics, and sometimes the combinatorics should be washed away because they're interfering with understanding global kinds of structure. And so I'd be very interested in having side conversations about that afterwards, like how this does or does not apply to what your worldview about what you're doing is. So this is the reason I'm here. The hat tile was the first known aperiodic monotile, which I'm not going to define just at this. Well, I will say something about it, but mainly the talk will kind of revisit these ideas as we go along. But basically the idea of an aperiodic monotile is it's a single tile, a single shape, but that can form tilings of the entire infinite plane, which means specifically that we have congruent copies of the tile that are fitted together without gaps or overlaps. And then so that means that's what the definition of a monotile is. It's a shape that can form a tiling of the plane. And then that it's aperiodic means that it not only can form tilings that have no repeat, but much more significantly and fascinatingly cannot form any other kind of tiling. It can only form tilings that, I don't know, I'm sorry. That's your thing. That's mine. Sorry. It can only form tilings that that cannot repeat. So it has this magical property of disrupting order in some sense at all possible scales, even though it's only fitted together side by side. But what's, oh, I don't know what happened to the picture, but it's one of an infinite continuum of aperiodic monotiles. I guess the picture is missing there. And then finally, we also, out of this came a chiral aperiodic monotile, which actually, there was some discussion of whether or not it counts if you flip the tile over or not, if that's two shapes or one. I think that's perfectly defensible that the hat tile is one shape in the way that tilers had looked at these shapes for ages and ages, but it does require that it flip over. And so just to sort of silence the critics, really, just by great fortune, there was another monotile that popped out almost immediately, which doesn't require flipping over. And I'll discuss all of that. But what I really wanted to talk about here is this more basic question, which has animated the area for decades. And I think is quite relevant here. It's just simply when you have a shapes in general and they're stuck together, how complicated of a question can that be? I don't think I have to sell that on this crowd as being incredibly, potentially very subtle. But but I really want to remind us that we're really talking about in a much more general sense. This is sort of a very universal phenomenon, both within physics and mathematics. So around the world, we have all kinds of things. Proteins would be like way up the list of like subtle ways that little things can fit together. But also even within mathematics, for example, logical expressions on a page, they fit together by certain rules that have to be satisfied in order for it to be well defined. This is I didn't want to put a COVID virus up, so this is some other virus, but the viruses, of course, are very much along these lines. This is sort of self-assembled from little plates that then are forming these larger plates that are somehow forming this shell.
Is that cool?
I don't know what, I've forgotten where I got this. I have this, I don't know really what this actually is, if somebody does.
I think that's a dinoflagellate.
Oh, it's a dinoflagellate, so it's not a virus at all. It's much, much larger. So yeah, that makes more sense because of the layers of structure. Yeah. So in any case, just to kind of give this some concreteness, we could ask, can copies of a particular shape be completed to form a tiling of the entire infinite plane? That is to say, without gaps or overlaps. Does this particular tile admit a tiling? That's the way we would say it, admitting a tiling. And I don't think this is much of a mystery. I'm pretty sure you've already in your heads visualized something like that. But then if we look at that, does that admit a tiling? And some of you may immediately have a proof that it doesn't. Does anyone suggest a proof? It's just simply that the only thing that can fit here is one of the points. And once you fit one point in, there's not room for anything else. So immediately it crashes. But then we get into things like this, which I have brought sacks and sacks of these to play with. This one, doesn't admit a tiling, and we can immediately, with some effort, or maybe not, it's not too hard to find a proof that it cannot form a tiling. And the proof is just, here's as much of a patch as it can form. It can form 3 concentric rings without getting any further. And you can see more or less what the problem is. You see on the outside, it's got all these sort of indentions all the way around. The issue is really pretty simple. The thing is, this is really a collection of 4 hexagons. And was there a pointer? So this is a collection of 4 hexagons, and each hexagon, some of the edges of the hexagon are fine, some are indented, and some are extended. And there are far more indented edges than there are extended ones. So if you just think back to what has to happen, if you think back to what has to happen, the number of, in the interior, every innie has to match an outie, so to speak. And so they have to be the same number of each. And so any imbalance in the numbers would have to be on the boundary of whatever patch that we're growing. If this patch is roughly circular, then the boundary is going to grow roughly like proportional to the radius of the patch, whereas the area, that is to say the number of tiles, will grow proportionally to the square, and any quadratic will eventually be any linear function. And here it beats it after 3 steps. And so this is the most, and this general argument, this will work. So this will go at most 3 steps and then crash. So that's fine. But here's an older example, which is pretty fascinating due to Robert Aumann. I guess this is kind of awkward with this modify thing. I didn't plan the slides this way.
There is a way to get rid of this.
Okay,
If you click on more,
I've lost my cursor too, so
that makes it difficult.
we'll go to
More on
the right.
and hide floating meeting controls.
Thank you. Wonderful. Okay. So back to this. This is Aumann. Robert Aumann was a fascinating person. I learned a little bit more about him during this hat adventure. So he was not a professional mathematician, yet he made many of the first rank discoveries in this area. And he worked as a mail sorter for his whole career. That's how he made his money. So, but nonetheless, this is one of the first important examples. This is again, kind of a deformed hexagon. The same argument shows it can't tile forever, but it can form these multiple rings. It cannot really form a 4th ring completely. You see these weird little gaps that must be in this 4th ring. This is the current world record for this kind of phenomenon. This is by Boschik. I apologize to him if he ever sees this, because he has some diacriticals on his name there. I couldn't get Apple to do. But in any case, this is now 1 tile, and then it's surrounded by 6 concentric rings of that one's miscolored. 6 concentric rings of copies of itself, and then no more. And so this at the moment is, in a sense, the worst that a non-tiling pile can do. The H number, it describes exactly this. The H number, if we just define rings as we have the original tile, and then we have a bunch of tiles that touch that one, and then we have all the darker blue tiles that touch the light blue ones, and so on. The H number describes how many of these concentric rings we can complete without any gaps. And so this would have H number 6. And as I said, this is the current record. And so it's an open question. Is the H number unbounded? That is to say, for any n, does there exist a single tile that has H number n or greater? And as I'll return to that question in just a moment. So here's another example, which I think I'd like to switch to the overhead for this because it's just too fantastic. Oh, sorry. No, I beg your pardon. I'm just kind of lost in the. So there's just going to be an extra 5 minutes built into the talk of just like me dealing with the setup. What I'm looking for is this. And I just wanted to show you this in person because this is fantastic. I would like to leave these out there for you to play with. This tile by Joseph Myers, who later is now a co-author, but I've known about this since he discovered it around 2003 by an extensive computer search. These are fantastic. This is really the problem. So like this little gadget does form tilings of the plane. I don't really know if it's humanly possible. I suppose like a highly motivated human with enough time could discover that this will tile the plane. I tested something like this with a slightly simpler example. I was at a conference with a whole lot of people that really like to solve puzzles. And I took advantage of that to offer a $100 prize for the first person who could demonstrate if the particular tile that I was working with could tile periodically. I knew it could. I knew the solution from Joseph Myers' computer search. And so I can say that a highly motivated puzzler who is seeking $100 as quickly as possible can, just as a benchmark, right? So I need some benchmark, can solve something like this in about half an hour, it seemed to me. So I don't know. I don't think this one is terribly much more complicated than that. So that's roughly how much computational power is required. And let's see here. This is the smallest possible patch that the smallest possible fundamental domain that these tiles can form a tiling with is this big. So these are even kind of mysterious. These will fit together if they're oriented the same way. These will fit together by, like so. So if these guys can actually tile the plane, though that's like really not obvious when you're standing here. And then in turn, with a little bit of effort, which I'm not going to do now, but I saw somebody at the table did the other day, pretty well. It's not too hard with this to figure out how to fill up one of these with these guys. Now, the real point is that this is the smallest, the simplest possible thing that this tile can do. The simplest one is that bad. And so back to trying to run this thing. So this flashed by, that's the answer. So this is Joseph Myers's polyhex. It has what we call isohedral number 10. Its isohedral number is 10, meaning that the simplest possible periodic, it does tile periodically, and the simplest possible periodic tiling has no fewer than 10 tiles within a fundamental domain. So this is the chunk that can be repeated, or a chunk that can be replicated across the whole thing. And this is again a world record. And the question remains, is isohedral number bounded? So this is also open. So the question is just how could you decide what would be a procedure for deciding whether or not a given copies of a given shape can be used to form an infinite tiling? And there's a really simple one that makes a lot of sense. It's just you enumerate larger and larger patches. And specifically what I mean by larger and larger, like you could enumerate like really long strips. That's not what I mean. I mean covering larger and larger disks, like actual geometric disks.
Kind of interrupted when you
Yeah.
said is isohedral number, like for a given tile is isohedral number.
Well, any given tile that does tile periodically has an isohedral number.
So the isohedral number is the minimum.
The minimum size fundamental domain, right?
Because I could imagine for that tile there's some complete.
Oh, yeah.
Even if it's not made from copies of.
Even
that.
from 2x1 rectangles, you can play those kinds of
So
things.
your question is about.
Given an n, does there exist a tile that tiles periodically, but its smallest fundamental domain requires at least that n tiles? So anyway, here's this algorithm that would just simply be to determine whether or not a given tile admits a tiling would be to enumerate larger and larger patches, meaning covering larger and larger disks. And if you cannot tile, then eventually there'll be some size disk that you cannot cover. Now that may or may not sound obvious. In fact, so let me rephrase it. So if a tile does not admit a tiling, then there's some size disk that you can't manage. The flip side of that is that if you can tile arbitrarily large disks, then you can complete a tiling of the plane. That's the composite. And that sounds really believable, but it's actually a little subtle. There's some actual argument there using some older stuff, but it's certainly believable. So if a tile does not admit a tiling, this procedure will halt and tell you it halted. But of course, if it does admit a tiling, this procedure will not halt and you won't necessarily know the answer. But if there were so returning to H number, if there were a bound on H number, which we don't know that there is, if there were a H number, then we'd also have another possible way to finish this decision procedure, because what would happen was we would enumerate larger and larger patches covering disks, and if we cannot tile, as before, we just run out of possibilities. That's the end. If we can tile, all we have to do is make sure we get up to that. Once we get past that bounded H number, then we're home free. Once we get past that bound, then we don't have to worry anymore. We know that, we can complete the tiling. So that's basically the connection between hash number and this decision question. Okay, but that's one possibility. Another is that as we enumerate patches, we can also discover if a shape emits a periodic tiling just by checking to see if we have a possible fundamental domain. So what we would do in the case of, say, the Joseph Myers tiles is we would just look around, and as we make larger and larger patches, we just check to see at every stage, and maybe within it, you know, maybe backtracking, looking at sub patches or something like that, to check to see, do I have a potential fundamental domain? And just as an aside, for this particular one, there's a wonderful fast thing called Conway's criterion, which is just a speed up in some cases, which I could describe later. So that's great. So if we can check in finite time, if a tile admits a periodic tiling or does not admit a tiling at all, that's something that our algorithm will halt in finite time and tell us that, yes, it did one or the other. So if there's no such thing as, again, an aperiodic monotile, so there's a whole bunch of vocabulary crammed into this paragraph. If there's no such thing as an aperiodic monotile, which again, reminding you that that means a single shape that does tile the plane, but does not admit any periodic tiling, then we'd have a method to decide the so-called monotiling problem. The monotiling problem being the question of whether or not a given shape admits a tiling. That is to say, whether or not a given shape is a monotile. A monotiling question, monotiling problem is just simply this: is this a monotile in the sense of being able to form a tiling of the whole infinite plane? Okay, well, so here we have it. The monotile problem, domino problem, the monotile, sorry, this is changed name somewhere, but this is another name for it. The monotiling problem is undecidable, implies that there exists an aperiodic monotile, and it also would imply that hash number is unbounded. Of course, at this point, we don't know that, and just, of course, the punchline was spoiled months ago. We know that there exists an aperiodic monotile on that end. And this is much more general. In general, the same basic layout applies when we have multiple sets of, like larger sets of tiles, the exact same comment. So if I want to know if a collection of tiles admits a tiling, then that's undecidable if there exists an aperiodic collection of tiles, for example. Page number is sort of less interesting in that sense. So it's amazing that aperiodic sets of tiles, that any number of tiles could possibly exist. I mean, I've been involved with this now for 40 years, and I'm not that old. I mean, old, but not that old. And so, like, I mean, it's still amazing to me. I mean, it really is amazing. It's incredible that this phenomenon occurs. And it's so incredible that the big bang of this is this paragraph here, which is essentially a conjecture that it doesn't happen. This was in the context of trying to wrap up this program from already 100 odd years ago of, well, let me just say from formal logic. There's something from formal logic. And so the idea is, you'll see shortly, that the way that, say, logical clauses fit together, logical symbols fit together, can be reinterpreted as the way tiles fit together, and that was this context. So the context here, how Wayne was saying, basically, that roughly translating this is that a collection of tiles, a collection of tiles forms the tiling if and only if it forms a periodic tiling. That's roughly what this says. And then if that were true, then there'd be a decision procedure to tell whether or not a given collection of tiles admits a tiling. And so that's to say, with a lot of specification of what we're actually talking about, a lot of the literature over the last 30 years is hidden in these 5 words of specifying exactly what we're talking about. But once we specify exactly what we're talking about, if the so-called domino problem is undecidable, that is to say, if there's no decision procedure to tell whether a given set of tiles admits tiling, then there must be an aperiodic set of tiles. And so let me just illustrate this connection. So Turing machines are a simple model of computation, and actually really any model of computation would actually do just fine here. But Turing machines give a very nice picture of what these are. So just to remind, or say what it is, So a Turing machine is specified by a little table like this, where there's some states that the machine can be in and some symbols that it's reading. We're on an infinite tape. The machine is in a given state. It's looking at a given symbol, and then depending on what the table tells it to do, if it's in state A reading to 0, it writes 0 on the tape, moves to the right, goes into state B, and indeed it does. Whereas everything else on the tape is unchanged. And we have this little time-lapse movie of what's going on. You know, really, this isn't really that different from, like, say, the way computer memory is scanned or something like that. So it's not, even though it's a toy model, it's really perfectly as powerful as anything else. And famously, the big bang of all of this is that Turing showed that there was no decision procedure to tell whether or not a given Turing machine halts, the famous halting problem. And here, halting would be if we happen to be in state C, reading a 1, we write a 0, go to left, and then reach the state H, but there's no H in the table. So that would just mean that we're stuck, and that's what we mean here by halting. So again, I guess it's worth reiterating that essentially the Church-Turing thesis has stood now for 85 years or something like that. And so far as anyone understands, there's nothing we might mean by computation that can't be emulated by a Turing machine. Quantum computation is a different mode of computation, but it's fundamentally the same in this sense. It's just a way of leveraging quantum mechanics. So in any case, given an arbitrary Turing machine, we can ask if anyway, never mind, don't read that. Given an arbitrary Turing machine, there exists a set of tiles that can form a complete tiling. If from a particular seed, we can ask, we can form a set of tiles that can, from this, once this seed tile is placed, all the other tiles have to faithfully emulate the action of the machine. It just looks just like that movie I just showed you. These tiles have to emulate whatever the machine was that I just did, as long as that one's placed. So it's basically just making a little movie. And it makes sense, because if you look back here, this is all just local rules. Just by a finite amount of vision, you can tell, does this picture look right? If there were ever a flaw in this whole infinite picture, you just by scanning around, eventually you would detect it. And that's exactly what tiles and matching rules are able to accomplish. So these tiles do admit a tiling if and only if the corresponding machine halts. This is sort of a generalized picture, I guess. But no, this is the exact same machine, actually. However, you can probably spot that these tiles, no matter what, do form a tiling of the plane, because sorry, wrong way. These tiles do form a tiling of the plane, yes, namely the blank one. So if it's not just that, this tile by itself can form a tiling of the plane, so that's a little stupid. But the point, this is not the domino problem, this is the so-called completion problem, completing a configuration from a given starting point. But this sort of building, it's quite subtle. It's quite a whole lecture on itself, really, to describe exactly how the domino problem uses this idea. Basically, the upshot is to show that to get around the seed thing, you basically figure out there's a way of constructing a collection of tilings where the seed is sort of everywhere. I can't really describe that quickly. So if we use more than one kind of tile, then incredibly, there's no method to determine whether or not tiles can be used to form a tiling. Sorry, another typo there. Can be used to form a tiling. In particular, then the domino problem is undecidable. And just as sort of in a finite world, which we really live in, roughly equivalently, there are all kinds of NP complete problems for finite patches of tiles. Meaning, so this is actually a practical application in some sense. So these puzzles are difficult and tedious, and moreover have no available theory, precisely because of this underlying connection to the theory of computation. So within a few years, Robert Berger, who another thing that was great about this whole thing was I got to talk to him on the game recently, which was nice. He came up with the first aperiodic set that famously had, over 20,000 tiles. And his hierarchical method really was the basis of a lot of constructions over the next half century. And so the basic idea of this is, so this tile here is it's a monotile. You can think of lots and lots of ways of tiling the plane with it, but it's not aperiodic. You can also probably think of lots of periodic ways to tile with it. For example, just taking two L's and flipping one around and making a rectangle, and good, there you go. But you can form non-periodic hierarchical tilings, which I'll explain, where there's a hierarchy of a sort, using a so-called tiling substitution rule, where we basically make the tile larger and subdivide, make those larger and subdivide. And in a sense, it's, again, I'm hiding all kinds of things, but in a sense, build these tilings in which every tile, say this red one, lies within a larger so-called super tile, within a larger super tile, within a larger super tile. And moreover, this is unique. And that's true of any tile. So I picked this one, it lies within an L, within an L, within an L, and so on. And why is this non-periodic? I mean, it certainly looks like the same everywhere you look, which it is. In fact, you can't distinguish any region of any one of these hierarchical L tilings from any part of any other. They all look exactly the same everywhere in some sense. But globally, they're different. There's sort of some global problems. Your eyes are probably sort of glazing over looking at this thing precisely because there is some sort of repetitivity. It's just not periodic. And it's not periodic in this sense. So when we overlay the hierarchy, you can see we have this hierarchy of larger and larger super tiles, these L-shaped super tiles. And if I have any given translation whatsoever, there's a super tile that's larger than that translation. Remember that the key property here was that every tile lies within a unique hierarchy of these L's. So if I were able to translate everything over, I'm sorry, I was hoping, okay, that's not as lined up as I would like it to be, but imagine this would line up better, then I'm really sorry about that, because what we should have here is be some L, if that were lined up, we'd have some little L tile that would both lie neatly within the hierarchy that contains this big L, and it would also lie nice and neatly within the hierarchy that contains this big L. Consequently, any tile in the intersect that lands, if this landed cleanly on top of it, any tile that lands is in the intersection of those two would therefore lie within two different hierarchies, and the hierarchy would not be unique. So the flaw with this picture is that I'm sorry, Keynote let me down. I wanted to have, so you have at least like one visible tile overlap there. In any case, these hierarchical tilings with unique decomposition are necessarily non-periodic. And so, I don't know what okay, never mind. So anyway, now the L tile itself is not an aperiodic monotile, but these guys are. And so this is from about the last time I went to a geometry. Actually, this is where I met Rock, and you were at Les Ouches in 1994, 5, I think, as well. So that's about the last. That's how old this is, and so that's when I more or less was able to show this off. So this is a example of a. Sorry, this is an example of a hierarchical tiling. So these little guys, through an elaborate combinatorial proof, which I want to say a word about, can only form these clusters, and these clusters can only fit together in exactly the same way, more or less, that the somehow that these can only, I don't know what I'm doing wrong. I guess it's flipped over. That these can only fit together to form larger and larger, like this arrangement, which I had a fourth one here, which it fell apart. But if I had a fourth one here, the arrangement of these guys can only be the same as the arrangement of the original L tiles. And this must continue ad infinitum. And basically the way that this works is that by some elaborate combinatorial just argument, one shows that the only way that these guys can fit together is to form these patches. And that these patches themselves are combinatorially essentially the exact same thing as a larger, as a big L. They're just, the way that these guys can fit together with a little bit of smudge in the middle, these little guys, is essentially the same, they can only do the same thing. And the clue here is basically that little bump corresponds to that little bump, that little indentation to that one, that to that. And everything else just kind of turns out to go along for the ride. Now, what's interesting is that this is prior to the hat. This was tied for, by many measures, the simplest possible, the simplest known aperiodic set. And what's fascinating, and I think very important, is that the proof that this actually works, the shortest proof that I know of, is really long and complicated and arbitrary and very ad hoc. And I think, and the hat tile is even more so. And I think that that's absolutely a feature that comes from this kind of theory of computation stuff. It's the same way that small, busy beaver machines, if you know what those are, have completely bizarre ad hoc seeming behavior. And in general, one expects that as you, well, it's actually not surprising that these very simple examples would have colossally complicated and unilluminating proofs, unilluminating combinatorial extensive proofs. And so we see that already in this example here. So back to hiding that and trying to return to Keynote, hit the play. So of course the most famous example is this one, the Penrose tiles. And here we have two distinct tiles. It does have a pretty simple proof. And the way you prove it again is you show that the tiles can only form, essentially they form larger and larger versions of themselves, which fit together in precisely the same way. So they can only form yet larger versions of themselves and yet larger and larger ad infinitum. And then here's another example by Robert Aumann. He came up with several of the most simple examples. One thing I just learned on this last month, because of all this engagement with the hat, is that I was talking to Penrose himself, and Robert Aumann, completely independently of all of this literature, just absolutely independently discovered this with and wrote Martin Gardner absolutely not knowing anything about, or like prior to Martin Gardner's article on Penrose tiles. And that what Aumann was interested in, the way he came to it was looking at, I guess he had connection to printing. So he looked at printer screens in 5 different orientations and was fascinated by the moire patterns. And from that, realized that he could form these tiles, and came up with these 2 tiles absolutely independently of the entire literature that I just sketched out, which is, it blows my mind, you know, to call him an amateur mathematician or to not a mathematician or something like that is just absolutely ridiculous. So unbelievable guy. So in any case, there's a astonishing variety of these kinds of tiling substitution rules, and just to sort of, and there's also no general theory of them at all whatsoever. In fact, given the combinatorial structure of one of these tiles, given an arbitrary combinatorial structure that might correspond to these tiles, it's not really clear how the abstract rules that define these would actually impose the geometry upon them. And that's a very, I think, one of the most interesting open questions that is totally unexplored. However, and here's another bunch of them. However, we do have, just to sort of advertise this. So the thing that's sort of started my career was basically I figured out a way to, given essentially any such rule like this, where, now this is not an aperiodic tile, but it tiles non-periodically. So given something like this, cooking up a way to put on markings and additional rules that then would create a new set of tiles that much like the one like these, the same way that these things force the L tile structure to appear. This is a very general theorem that for every asterisk tiling substitution rule, there's a set of marked tiles that can do that. So obviously, mathematicians being mathematicians, we want to get the number down. Does a single tile suffice? I don't think it's too much of a mystery where this is going. So we know this is Dave Smith. He's a fellow, and he is a so-called amateur mathematician. The word amateur in English has been debased to the point where it's unrecognizable. Unfortunately, we don't have a word to replace it. So the original meaning of amateur, of course, is love, or someone who acts out of love for the subject, performs at a very high level. And I've thought over the last few months a lot about why amateur was debased and professional was upgraded. It's obviously because the professionals were trying to take over. And so we don't really have a way to refer to what he does. But
I suggest,
yeah, sure.
At least until when I was a young person, the Olympics, you
Yeah,
had to be an amateur.
that's right.
How about the Olympic?
Well, I don't know. I don't know how much effort he put in. But I got, one thing is to emphasize too, is that there was nothing accidental about this, that he had a very specific. So what Dave does is he likes to fool like this. He prints out tiles, he cuts them out, he knows everything that's going on. All these examples I just showed you, he's played with. And that's how he enjoys his time, spending his time. And he had a specific idea that there was a specific place to look that nobody had really examined. And among these so-called polychites, and there's a short list of somebody else had come up with the polychites, these so-called polychites that were confusing and strange. And he looked there and presto. So this is what he contacted Craig Kaplan, who had a program for generating large patches of tiles. And then Craig amazingly was able to see some structure in there. And we're off to the races because, there's a number of ways of organizing this proof, but the first version, the version that's in the published, or the preprint at least, is this one, which is that the tiles can form into these so-called metaclusters, and then these clusters themselves have a substitution rule upon them. The hard part of the proof is to show that the tiles must only form that any given tiling by the hat tile has to form these in a unique way into these clusters. And so that's where this unilluminating, extensive, computational, computer-based proof comes into play. Is just to sort of check by examining small patches that this can be uniquely, any given cluster of hats can be uniquely decomposed into that. And then from then on, it's actually pretty straightforward to show that, okay, they can form these hierarchical structures, which I'm not going to get into, and that they moreover must form these hierarchical structures. So what I'd like to take a little time to discuss, because for a more general talk, I'll be able to go into the hat tiling. So, and I'd like to just go into a couple of technical things that'd be more appropriate maybe here. So quite astonishingly, Dave wasn't, Dave, this is just like the gift that kept giving, honestly. So Dave produced a second candidate, Einstein. Oh, I should say something about this word. So Einstein, I apologize for. It's not any of us, so Ludwig Donzer coined this term for this aperiodic monotile 30 years ago, and he did it deliberately for the publicity value, and he was laying the ground, and of course it worked tremendously. It's also really embarrassing and kind of hokey, but nonetheless, fine. So he produced a second candidate, Einstein, and this one, but it turns out to be combinatorially equivalent. And so you might have seen, if you've seen this at all, any of this at all, you've probably seen this movie, which is running through this entire continuum of possible tiles.
So does that mean it suddenly gets very simple at one?
Yeah, so that's right.
There.
So
Like
there's three tiles in this movie that are not aperiodic. There's this one. So what's going on in the movie? There's basically two edge lengths. One of them is doubled. The long edge is just a double, one of that one, I guess, something. I don't know, I can't really tell. So there's two edge lengths, and it's just the ratio between them. So as the movie's changing, we have various things. With one spot, one of the edge lengths goes to 0. At some other spot, another edge length goes to 0. And somewhere in the middle, the two edge lengths are the same. And these three spots.
When the edge length is 0 and it looks really simple, like chevrons.
That's right.
Are those also?
No, so these have more ways they can fit together. And so including a periodic way. But anywhere where the edge lengths are distinct and non-zero, they behave exactly the same way as the hat tile. It's exactly the same tiling in effect, as you can see in the movie. The one exception is in the middle, where the two edge lengths are equal. This will also tile periodically if we allow ourselves to flip the tile over. And so this was the specter. The specter, in this tiling, some of the tiles are flipped over. This tile will tile periodically if we allow it to flip over. If we remove that possibility, that's where the specter comes from. So that's basically the family. So we have this infinite continuum with these two bad endpoints, which are always allow periodic tilings, and this one special spot where if we don't allow reflections, it'll also be aperiodic, which is, again, more than anyone really could have remotely expected. I mean, seriously. But even better, Joseph produced a second new kind of proof, and there really are very, very few proofs available that shows why this is aperiodic. And so suppose there were a periodic tiling by the hat, then we would have some sort of lattice. Now, obviously, you missed the joke, it's covered by the artistic license is necessary. It has to be necessary, right? Because there is no periodic tiling by the hat. But in this grid, we have a lattice of some sort of fundamental domain that's being shoved around. And okay, so now this does tile periodically on its own, and this tiles periodically on its own. That's not the point. The point is that if this had a periodic tiling, there'd be an exactly the same combinatorially equivalent tiling by this, and a combinatorially equivalent tiling by this one. And with some with some very careful arguing, which really is necessary, you can show that the shape, now that they have periodic tilings, the periods may be very different. I mean, the aspect ratio may be totally different, but with some effort, one shows that they have the same, that it's just a similarity. And since we can normalize everything, we can just say it's exactly the same. So with some effort, we can say that these other periodic tilings would have to have the same exact period. And here's the contradiction. They have the same area because they have the same number of tiles. They have the same, but the chevron can be divided into 4 equilateral triangles and the comet into 8. So we would have a periodic tiling of triangles, a division of this up into triangles and a division of this up into triangles that has the same period. But the triangles here are twice the area of these, and hence have square root of 2 scaling. And so with that, we're done, because you can't overlay 2 triangular tilings with square root scaling in a periodic fashion. So that's fantastic. And to make a point about that, there are very, very few known proofs of aperiodicity. Even though there's some decidability results at the bottom, which assures us that we will never run out of possibilities for proving aperiodicity. In practice, the hierarchical method that I showed you is really the main one that we know much about. So I'd also like to just take a few minutes because of this seems appropriate for this group. So a very practical question with all these aperiodic tiles, if you've ever played with Penrose tiles or anything else, or the hat tile even, you would realize very quickly that you will get messed up and you'll get stuck and you won't really have any help, and you might feel stupid or like frustrated or whatever, but rest assured, it's not you, it's a theorem. So it's actually a theorem that no local rule, okay, so there's a lot of asterisks there, but no local rule can be used to assemble not only just the hat, but in fact, any aperiodic set of tiles cannot be assembled reliably into an infinite tiling. This is a very powerful theorem by Dworkin and Shea from 1995. So the reason that this is important, this is particularly important, what they were after was that when quasi-crystals were discovered in 1981, their resemblance to Penrose tiles was very quickly noted. In particular, the diffraction patterns of Penrose tilings, or the three-dimensional analogs of Penrose tilings, are very much akin to the diffraction patterns from many different kinds of quasi-crystals. And so immediately the question is, well, okay, if atoms are somehow making Penrose tilings, how are they doing it? How are they sticking together? By some, presumably atoms are just fitting nice next to each other, right? And so the rule, the kind of idea we would have would be by perfect local rule with all those asterisks. What I mean is a rule that would take a finite, you have some finite window and you scan around, and by examining that window, you can determine what the right tile place is. And you move the window and you place a tile and so on. And they proved it can't work. And I'm going to show you the proof. There are a lot of ways around this. That's why I put all those asterisks there. So, for example, there's probabilistic ways of doing it. There's ways to doing it that's perfect within any epsilon of perfect. There's ways of doing it using signaling. There's ways of doing it where you allow yourself 2 layers, all kinds of things. But just strictly looking at a finite window and scanning around, that can't happen. And here's the proof. So suppose that you have a finite window. Suppose that your window is this big. I'm going to have a rule that's going to assemble hat tiles, and then I'm going to only look at patches this size. And because of the way that this is true for any of these hierarchical tilings, but it's also true for any tiling whatsoever by a very deep theorem by Radin and Wolff, that in any tiling, any tile that admits a tiling in which there are patches that are repeated infinitely often. But actually, we don't even need that. We just need 3 of them, because if we can find a tiling where we have 3 of the same patch, have the size that you want. Remember that we were given the window size. So this is the window size that I want. There are 3 patches of this size. And then I just, okay, so something went wrong with the keynote. I wanted to show you the middle picture, because I'll just have to say what happens. So then what we do is then we also have tubes of tiles that connect from here to here. And then given those tubes, which is probably the picture that's directly underneath this one, we can then form a lattice of, you see, the way these tubes work, right? The tube connected from here to here. So in particular, this end of the tube could just be stuck on that end of this patch, right? So once I have those tubes, once I have this connecting this and this connecting this, then I can then actually, that gives me a way of filling out the whole, like connecting this up into a lattice. Now, consequently, this thing cannot be completed into a tiling, because if it could complete that, because obviously if I could fill that in, then I could form a periodic tiling. Well, I can't form a periodic tiling. So that means that just by examining local patches, this all looks fine. This all looks great, but I'm screwed. I can't complete this. And this is a very general argument, which applies, it's frustrating. It really is frustrating, because you're trying to make these things. So, and in particular, last month we made, I forgot to put a photo of this, but last month we made a big floor out of about 1,500 tiles. And in a couple of weeks in Newcastle, we're going to try it again with a different collection of tiles. And so part of the question is actually, how do you actually practically get a crowd of people to make one of these? And so what you do is essentially this, same as what I was demonstrating here. You make the super tiles, you make the super tiles into larger super tiles, you make the larger super tiles into larger super tiles too. That's not a local assembly rule. So it doesn't violate anything. in any case, there was all sorts of kerfuffle about whether this was a single tile or not. And I think this is a wonderful puzzle to find the reflected shape. But I think it's also a good argument for the fact that, you know, if you can't actually tell, then it's the same shape, right? So then, but in any case, I think, so a lot of you are working in three-dimensional chemistry and stuff like that. So, or three-dimensional objects, obviously stereoisometry, it really matters, like stereoisomers, it really matters left and right-handedness in three-dimensional physical objects. But there's a long tradition in the plane about that when you flip things over in the plane, it's the same shape. And really, in fact, arguably, this is already in Euclid book 1, prop 4, where he discusses side angle side theorem for congruence of triangles, and quite clearly takes the stance that two triangles, if they're reflected copies of each other, are congruent. I mean, you just read, it's right there. So, but just anyway, we were fortunate to short circuit all of that. They've noted that that middle thing, the 1-1, where the two edges are equal, allows the possibility of not allowing, just if you, it has additional, so having the two edges equal allows additional combinatorial flexibility, that then you can remove some of that flexibility back by no longer allowing reflections. And then that just happens to be right on that special knife edge, by good fortune, where this is 2 in aperiodic tile. Because it has no reflections, we can modify the edges with many exciting possibilities. And this is now just some fun stuff. So this is Rob Battauer. If you caught any of this, then you saw a lot, you might have seen a lot of this kind of stuff. This was really, I'm not on social media, so fortunately, so I was getting all this secondhand, but it was really quite amazing what was going on. So in particular, I'll come back to that. Within a few days, we saw all of this. And then the excitement, of course, was just incredible. About the shirt tile, the shirt hat controversy, yes, it is a shirt. It's just unfortunate that 2 of my co-authors saw it as a hat before anything else. Just an incredible array of art and stuff. This is an interesting question about, I was wrong. I thought that this wrapped around because see, Dworkin and Shea's proof also says that any tile that tiles the plane, any collection of tiles that tiles the plane, for any width, there is a strip, a periodic strip of that width is possible to form. Because it's just a modification of Dworkin and Shea's proof. And so it's simpler because instead of doing the lattice, you just go in one direction. And so actually I thought that this wrapped around the back of the can, but now not.
Interruption. I remember this question came up in the rollout and all that. It's very question about strength and so on. It was part of the scientific discussion as you were.
Yeah, and I didn't know this argument. I didn't realize that argument until after.
But this can was available for it. Yeah.
No. So I think that's a little extreme. But.
So you think you could find a piece of the pattern that would wrap around a cylinder?
Yeah, the problem is that you can't control the aspect ratio. So it's true that for any width, you can find a periodic strip of that width, but the width will grow, the length will grow. Like it won't, like to expect a strip of this width that wraps with that period is probably unrealistic. But
Still interesting.
but it is interesting, yeah. It's an interesting phenomenon.
It has a seam on the back or something that it's not.
Yeah, this does not have that. Yeah, this has a seam on the back. But there are some nice, beautiful examples. So it'd be suitable for toilet paper. There's a story there. Penrose, I don't know if you 25 years ago, Penrose sued Kimberly Clark for infringing on his patent on Penrose tiles because they had a Penrose tiles themes and toilet paper, which is kind of cool. And we can only hope. So in any case, just to sort of put this out, because this is this is very visible in certain parts of the public, there is going to be this contest, which is opening now, where people can submit their own designs of this kind. It's not just the hat, it's also for the Spectre, and there's actual money. It's not just 20K, it's actually more than 20,000 pounds in prize money. So that's pretty amazing. And that's the address for that. And I think that's really all I have to say. I have lots to say. One thing I'd just like to say in conclusion, though, is that these tiles are really great, and I'll leave them out there to play with, and I hope that you'll get your hands on them, because it's just a lot of fun, and that's really
Cool.
One thing I said that I at the beginning was that with the Oppenheimer baby, Oppenheimer's penchant for wearing a pork pie hat, that you might want to try to Photoshop that on the head
I've already seen it with Einstein.
right.
And they're so stupid. Like there's like all these like pictures of Einstein.
Ask you a serious,
Ludwig Dons are really finally.
let me ask you a serious question. So the issue of periodicity, meaning you can tile porous.
Yeah.
I mean, I want to talk about this in private, this one of the things. So besides these sort of logical combinatorial kinds of things, sometimes complex analysis comes into play. There's things about doubly periodic functions. You can find a way to connect it with the homomorphic function or sections of them.
I mean, you could concoct.
Yes, so it actually works for a problem that John Sullivan was asking me just before a workshop with the Dennis organized at the actual 21 years ago. He'd been asking me for months about a problem about triangulations of the torus with a single five and a single seven. And finally, at Dennis's insistence, he did this, what was it, a Bell session. I gave a talk that had Abel's theorem as a pun on that at the end. It didn't give the whole deal, but at the end, we figured out how to get a proof of something that was actually known for actually more than 30 years of quantum Dennis's thing, but it was a complicated combinatorial proof. We became a one-line proof using the properties of the function. So I don't know if there's some connection here. These seem very different because they seem to involve deep questions of computational complexity.
The complexity is a big part.
And when you drew the picture of, almost getting some drug, there's a hole to fill in.
Well, there's another really important distinction, which is the difference between so non-periodic things are just there in front of you, right? And non-periodic structures are sort of I don't know how to put it, but the point is that these, you're really interested in the local combinatorics of what is allowed to be next to what, and so that has to be built into the problem to make any kind of translation.
I don't want to dominate this because an analytic function in the plane.
Yeah,
Once you know what's going on in the place, it does what it does.
that's true. That's another key
And if
difference.
it fails to be periodic. That conceivably can be detected from.
Well, see, that's another key difference is that these always have uncountably, rather than one distinct thing that can happen. It's uncountably many, and so there's no control.
Yeah, so that could be
So that may be another. Yeah,
But who knows?
because the local information does not, for some, like you saw with the L tilings, the local information doesn't actually tell you where you are at all.
Actually, I'm talking, it's not that, actually, I don't
Yeah.
think what you just said would be an abstraction of this idea. But
Yeah.
It could,
Yeah.
let me stop.
All right, well, we'll talk more.
This may be a very naive question. Maybe it can be proved that can't be true. I mean, so what I took away from the monotile aperiodic tiling proof was that you construct a larger pattern composed itself of possibly several mesoscale patterns of the elementary tile, and then that thing scales.
That pattern,
That
pattern, the things that they can form can only form larger copies of the same thing
exactly
again.
larger copies of
And then of
themselves.
course ad infinitum, yeah.
Is it clear that it's impossible that you could have something that forms larger copies of itself, but always with different mesoscale?
Yeah, we were
Times.
wondering, well, yeah, I think so.
So that would be kind of
Yeah. I mean,
qualitatively different, right?
let me say that the hat, this is the first proof in the literature where we even have some sort of crazy intermediate structure. Okay, so that this phenomenon never appeared before. So one might expect, I mean, in biological systems, we see this all the time, right? That somehow structure at one level forms structure at another level, forms a totally different structure. So this is our starting point for that question, right? I mean, what I would guess now that people know that this is something to look for, that over the next decades, we'll just see tons and tons of this, I think.
Okay, I'm hungry. Let's take time again.